Okay, we're going to work on the dot product of Cartesian vectors. And actually, we should also write the dot product along with what we have down here. So A dot B would be the equivalent of the magnitude of A times the magnitude of B.
The dot has to be circled.
Sorry?
The dot has to be circled.
I just make it that way so it looks different than, sometimes the dot is used in multiplication, but this isn't a time, well, kind of is, but this is, they consider it the dot product, right? So I make it a circle to differentiate just a little. And in this case, they've given us Cartesian coordinates for vectors, okay? So this is the component of their horizontal and vertical components to build that vector. What does that mean? Well, we're going to build a little Cartesian plane here. Okay. Our Cartesian plane. And I should have built this larger because my values are bigger. I should have just used smaller values. That would have been easier. But what do we got here? One of them is a horizontal of 6. So 1, 2, 3, 4, 5, 6. So imagine this as the horizontal component of this vector. Okay, and then the vertical component of the vector is the value of 2. Okay, so 1, 2. This is the vertical component of the vector. We go up 1, 2, and think of this kind of like a bingo sheet. We just go horizontal and vertical from there, and this is where the head of the vector is, and the tail of the vector happens at the origin. Oops, I want that to be black. So we've built one vector here. Another way to have visually done that is if you just take the vertical component and move it over here, then you can see where it ends. Very similar to the addition of vectors. So here's one of our vectors, and that was vector A, I believe. Vector B, here we go, -2. Okay, so down negative, oops, this way actually, -1, -2. -2, I'm going to have to extend this a little this way. -3 and -4. I know it's going to go down to -4. Horizontal component was -2, so same idea. I'm going to use our little red line here to go -2. And then the vertical component of this same vector is -4. So we go down to -4, kind of like a bingo. Bingo the right term? Yeah, like bingo when you're going rows and columns. This is where the head of the vector will be. The tail of the vector will be at the origin. And here is our two vectors. Now, when we look at these vectors, they are pretty far apart. Okay, so we have value of b. I need the magnitude of these vectors. Okay, luckily we can use Pythagorean's theorem to figure out the magnitude of these vectors by using their vertical or horizontal components to build right-angled triangles. Okay, so I'm going to build them off of the x-axis because if you've ever done trigonometry with the Cartesian plane, we're always building from the x-axis. So let's do, this is 90 degrees, and that is 90 degrees, which then means this has a distance, think of this like a distance of 6, a distance of 2. This has a distance of technically -2, but when we put into Pythagorean theorem, because we're squaring it, it's going to be the, all intents and purposes, it'll just be 2, and this is going to have a value of technically -4, but again, Pythagorean's theorem. So we use Pythagorean's theorem here. We're looking at vector A is going to be equal to, or the magnitude of vector A is going to be equal to the root of 6 squared plus 2 squared. Okay, that's going to give us the root of 40. Yeah, root 40. So magnitude of vector A is root 40. Magnitude of root B, or vector B, is the root of -4 squared, put the proper values in, plus -2 squared. That's going to be 416 root 20. So absolute value, or the magnitude of vector B is 20. Great, now that we have the magnitudes, we need the internal angle. Now, technically there are two angles here. Okay, so which one do we want to use? We focus on an angle that is less than 180 degrees. From our visual, that looks like it would be this angle here. Okay, but we're going to have to piece it together with some information. I know that the distance from here to here is 90, so I got part of the angle. I then need to find this internal angle here, figure out what that is. And this external angle here will also help us, okay? Which, in order to solve that, I'm probably going to need this internal angle over here first, and then subtract it from 90 degrees. So quite a bit of work with the angles to do. We know this is 90 here. We can use, because again it's a right angle triangle, we can use our tangent ratio. Tan theta, that's for this one here, is equal to the opposite, which is 2 over 6. So theta is equal to tan inverse of 2 over 6, which is 1 over 3. Whoops, said 3, 2 over 6. We'll figure out what that is in a second. I'm going to do me a favor and just calculate it on this calculator. And on this page here, same concept. We're looking at tan theta is equal to opposite, which is, again, -4 and -2, but because they're both negatives, I'll write it in this way anyways. -4 over opposite over adjacent, -2. It's going to be 2, so
That was 18.4.
what is it, sorry?
18.4.
18.4? 18.4 degrees. And here we're going to have tan inverse of just 2, of the value of 2. So what will this?
63.4.
63.4? Okay, so this here is 63.4 degrees, but we actually need the external angle there. So I then have to take 90, subtract it from, I'm just going to do a little bit of rounding. Should I do some rounding? Yeah, I'm just going to make these whole numbers, okay? You can be as exact as you want, but we want to do this a little quicker. This is looking like 27, and that one we're just going to say approximately 18 degrees, okay? So this angle here is 27 degrees. So the internal angle is the addition of 27, 18, and 90. So our internal angle here, we'll call it theta, is 27, 90, and 18. 135? Is that what it is? Okay, beautiful. So it's 135. Great. Now we can apply it to our dot product here. So A dot B is equal to magnitude of A, we said was root 40. That's a 2. 40. And I don't need to have absolute values around that. Magnitude of A is root 40. Magnitude of B, root 20. All times cos of 135. 135, I think we should know. It's 45 degrees, right? Be a negative value, 45 degrees. I should know this off the top of my head with trig. What does it end up being, that value?
-20.
Negative 20?
Well, the whole thing's
Oh, the whole answer is negative 20? Okay, so it looks like we have negative 20 joules in terms of our dot product between these values here. Or Newton meters? I think it's Newton
Joules.
meters. Joules or Newton meters, I think it is, for a measurement. Okay? So there you go. You got your values. Quite a bit more work on the Cartesian vectors than when they actually give you the magnitude of a vector.